Okay, hello guys. We are now at the final stretch of this course. We're going to have two more lectures and one more practical, and then we're done. Okay. And in this is my final lecture, and I wanted to sort of show you examples of how thinking critically about the dynamics of the system that we're studying can lead us to develop better models that make better predictions and tell us interesting things about the systems that we're studying. So this is a full example class. I'm going to walk through 3 examples in increasing complexity. And hopefully in the final one, we'll get to see some new concepts that will hopefully inform a lot of the models that you see in the wild, okay? I'm going to start with 2 more simple models that sort of illustrate the point that I'm trying to make. And so the general topic then is this idea of using the particular characteristics of the system that we're studying to develop better models, right? It's actually using our scientific information about our systems to really do better than using standard things, right? So I'm going to start with, this is called the golf example, and this is a didactical model from Andrew Gelman's group. And at some point they got this data set, which is probability of hitting a golf ball. So this is measuring the distance from the ball to the hole and measuring the probability that a golf player will hit that ball in the hole, right? And so these are probability measures, right? You can see the sample sizes here, like the number of I think this is trials and successes. And this is the distance from a hole in feet. And as expected, right? As you get further away from the hole, it's harder to hit the ball, right? And the question is, can we model this relation? Like, what is the predicted hit rate given a distance for these golf players here, right? And so this is a fairly standard data set, right? You have one linear predictor. You have what I hope you all can identify as a variable that comes from a distribution. Which distribution would this variable come from? Number of trials and successes. Which distribution would you choose? Binomial distribution. Is it clear for everybody that this is like a classic case of a binomial variable, right? You have trials, you have successes, and you have some predictor. So you walk into this problem and you say, well, okay, let's fit a binomial regression, right? This is what should be pretty automatic. At this point, you have here the number of trials, the probability that you're trying to model. You use a logit link function, and you use a linear predictor that has the x predictor here being the distance from the hole, okay? Would this be your first impulse when walking up to this problem? Does anybody disagree with this, or would try something different immediately, or having a data set composed of successes and failures and a predictor? Would you gravitate towards this? Okay. Does it seem unreasonable for anybody? Okay, good. This is the model fit for the logistic regression for this data set. And it captures like some aspect of the data, right? It decays at a reasonable rate. But it also, it misses almost all of the points, right? It's got a pretty crappy fit to this data. It has this weird behavior where, like, at distance 0, where the ball is already inside the hole, the model predicts that you're going to miss a few of those, which is kind of weird. And the shape is okay, but what I'm proposing is that we can do better, right? And so what these guys came up with is sort of a geometric model of this. How can we describe this system in such a way that it makes a little bit more sense? So let's think about the mechanics of this. What's happening, right? So the hole is over there, the guy has the ball here, and he's gonna hit the ball, and he's gonna try to hit the hole. Why do you miss in these cases? Yeah, you hit at the wrong angle, right? So you want to hit directly on the hole, but it's hard, right? It's far away. You have some leeway on how you can hit the ball, right? And so the description that they came up with is to think about the geometry of this thing. So if you think that the ball is here and the hole is here, there's sort of a maximum angle which you can miss and still have the ball fall in the hole, right? And this is dependent on the radius of the hole and the radius of the ball, right? And if the ball misses too wide, it will miss the hole and fall outside. And there's some angle here that's related to the difference between these two ratios here, right? And we want to do statistics, so we might put like a normal distribution on the distribution of angles here. So the player has like a target angle that he wants to hit, but there's some noise in the way he hits, right? He's aiming at the middle, but he misses by some amount. And the amount that he misses by, you can sort of approximate that with a normal. And so the idea is to, looking at this distribution, there's some core here where if the actual shot is in the middle of this distribution, you will hit the ball. And if it's outside, you won't hit, right? So what you have to do is sort of use the cumulative distribution to integrate up until some point here, which is the threshold, right? So there's some, what's the probability of hitting the hole, right? You integrate up until some critical angle here, and then you calculate the rest of the core of this distribution to get the probability. The shape of this looks like this. So the probability that the angle is less than something is a cumulative normal distribution up until some angle. And then you multiply by 2 because you have the two tails. There's one tail on this side, one tail on this side. And then you subtract 1 to get the core, right? So this is the intuition behind this equation here. You're just trying to calculate what the probability mass is in the middle of this distribution of shot angles, right? And if the probability is in this region, then you hit the hole. So that is the model, right? And so you just plug in that expression for the probability into this. So the distance is here, right? It's how far away you are. That has like a sine relation with the angle, right? As you're far away, the region, like the angle increases, and the region of the distribution where you hit the ball reduces, right? As you're far away, you have to hit closer and closer to the angle so that you still fall inside the hole, right? That's the intuition.
But where is distance again?
It's here.
Ah,
So this is the,
radius of the ball?
yeah, this is the opposing side of the triangle. This is the adjunct, I don't know how to say this in English. Oposto e adjacente. Né? So you take the sine of this angle here and you get the critical angle. There's some variance here that you're going to estimate, which is related to the precision of the player, right? And so this model has one parameter. It's just the variance of the shot, the angle distribution, like how precise is a player in this data set, right? And if the player is very precise, if the variance is small, then he's expected to hit balls very far away. If the variance is large and he can't really hit the angle that he wants to hit, then you get a very steep decline in the probability of success here, right? So there's a single parameter to fit. We can write this model in Stan. I put this Stan code here just so you guys can get a sense for it, but hopefully you can see that this translates very easily to the Rethinking package, right? You would just write something like this in the Rethinking. There's a bunch of parameter declarations here that is just fluff from the Stan point of view. But it's just writing a direct translation, right? So the probability P is some cumulative distribution here and some threshold angle, and the only parameter here is sigma, and then a likelihood of hitting the target given this probability that is basically given by these curves here, okay? And then we can see the fit of the geometric model. And it's much better than the binomial model, right? Yes?
Can that be considered overfitting?
Can it be considered overfitting? Well, I don't know. You only have one parameter, right? It's hard to consider this overfitting with a single parameter, right? It's just, you're making a geometric assumption, right? So maybe this assumption is kind of wrong, but it's a clear improvement over the logistic one, right? You're capturing relevant aspects here. So crucially, if the ball is very close to the hole, it's very easy to hit, right? So if it's in the hole, you already hit it. And this decay looks a lot better than the logistic one. So this is a model that makes better predictions with less parameters by using relevant aspects, physical aspects of the system that we're studying, right? And I will leave this link here if you guys want to see this example. They go further with this. They find after they did this for a while, they found a new data set, so they found a larger data set to test this model in, so they do cross-validation. And they get excited, so they add the velocity of the ball in the model, right? So if you hit it too fast, it will also, even if you hit the ball in the correct angle, if it's going too fast or too slow, you won't hit it, right? And after adding velocity, this model gets even better. So like including more scientific aspects will make this even better. And I will leave this link here for you guys to look over because it's a great example of sort of thinking critically about models and testing predictions and looking at model convergence and things like that. Any questions on this? Okay. So now, just because I said I was going to do it, I'm going to do it. I'm going to show you guys that it's possible to fit models that use differential equations to do predictions, right? So in the Stan language, so I'm going to use this data set of bacterial growth data. So this is a bunch of measures of light absorbance, right? So as bacteria grow, they absorb more light in solution, and you can measure the number of bacteria by measuring the light going through a solution. And there's a lot of variation across different vials here. So depending on whatever characteristics of these vials, you get different saturation points here in the growth of the bacterial population, right? Hopefully you can all recognize this as an example of a logistic model, right? So you have an initial exponential growth rate and then some carrying capacity here that's related to the characteristics of the environment where this population is growing in. Okay, so let's fit a logistic model to these growth curves. The logistic is sort of cheating a little bit because you can just use the solution, right, and fit the solution directly. But assume you're using a differential equation where you don't have the closed form solution, right? You can only express the relation between time and the population using the differential equation. And in this case, what you have to do is, in Stan, is define a function that will encapsulate the differential equation. So you guys have been working with differential equations integrators with Renato. This is exactly the same thing. Stan has one of these built in. And so there's some annoyances with the parameter names that you have to use. So all of the parameters have to be in a single vector, so it's a little bit confusing sometimes. But in this case, the two parameters of the logistic growth curve here, the growth rate and the carrying capacity, are the two positions in this theta vector here. if you had a differential equation with more parameters, you would have to put a larger theta factor here to describe your equation. Hopefully this is very similar to what you guys are seeing in Python, right? Is this completely alien to somebody, or is this reasonable? So this is the dy dt term here, right? And all this thing does is move it forward in time here. Okay, and then in your model block, you can use an integrate ordinary differential equation, Runge-Kutta 45 here, which is, I don't know if Renato talked about the different methods of integrating differential equations, but Runge-Kutta is a popular one, works fine. And then you just use the function that you defined and some initial parameter values here, the vector, the theta parameter for the differential equation parameters, right? And measurements here. So these are the growth, observed growth and time measurements. And we use this differential equation to define an expected mean. And then we use, this is the measures of absorbance in each vial. So T here I is looping over vials, T is looping over time, and each observation has a normal likelihood with the mean given by the differential equation. And then you set priors here for the parameters. In this case, the parameters for the differential equation have a Cauchy prior. A Cauchy distribution is a distribution with very fat tails. So if you're really not sure where your parameter is, sometimes that's a good idea. It normally isn't. It's usually better to use something with less heavy tails here. And then the variance here has a very tight prior, in part because the variation is very small here. Oh, so there is some variation around some mean here, but it's very small. And this is encoded in the prior by using a very small standard deviation here for the prior of the standard deviation of the observations, right? And this will fit pretty well, and you can fit differential equations to those time series there. And again, I will leave a link here for a larger example of this if you guys are interested. But you can use these in your project. If you're using a differential equation in your project and you would like to fit it to data, this is one way to do it that works very well and allows you to make use of these priors here to sort of limit the parameter values that you're interested in your differential equation models. Sometimes fitting differential equations is very difficult because the estimates are a bit unstable, right? You have many possible values, and some of them it's hard to integrate, and you get weird behaviors, and using tighter priors can help with the model fitting. So this is, I recommend looking through this if you want to use this sort of time series model fitting using differential equations in your projects. Okay, any questions? Hopefully this is very straightforward, right? We're just using an integrated differential equation to get the expected value of a usual normal distribution.
So at the end we will have a distribution of parameters, and we can also think of a distribution of each point in the line, right? The curve.
Yes.
Yeah. So what is the better estimation? What would you consider the better estimation? Like the mean of each point or the mean of the parameters?
Well, these are different things, right? One of them is sort of the predicted curve for that point, right? And the other thing is the distribution of the parameters. So some questions we're going to use the parameters. So for example, are there different growth rates across different vials? And then you would have to look at the distribution of parameters. or if you're interested in the actual number of individuals, right, final number of individuals, then you would look at the predictions, right? So that depends on the questions you're asking. If you remember from last class, the monkey example, a lot of the inference happened in the parameter scale, right? I didn't show you any predictions from that model because all the questions were related to the parameter values. The example I'm going to do next, we're almost not going to look at the parameter values. We're just going to look at predictions because this is what we're interested in. Okay? Yeah.
So if we wanted to check if our model makes sense, could we plot samples from this?
You could, yeah. So one thing this post here does is iterate over this model, making it more complex each time and comparing the model fit to the actual curve data. So once you fit the parameters, you can generate predicted values, right? And then you will get predicted growth curves for each vial, and you can compare the two, right? And in this case, it's interesting. One thing he doesn't do is partial pooling. So you guys could use this data set to implement a partially pooled version of this, where you have growth and carrying capacity values that are now informing on each other, right? And then you will have an estimate for each of these vials. If you look at this model here, it's mostly independent, right? It's actually fitting a single theta for all of the vials. So this would be a completely pooled model, right? And you could modify this. Hopefully you can think about how to do this to have a different theta value for each vial. Right? Does that make sense? So in the same way we did with the archipelago example in practice class today, you could have a single slope and intercept for all of the island groups, a single growth rate and carrying capacity for all of the vials, or you could estimate a different growth rate and carrying capacity for each vial using a similar strategy. Just allow the parameters of the differential equation to vary with the vial. Okay? Any questions? Okay, now I'm going to move to the meat of this lecture, which is the Pacific Island Tools dataset, which is a very cool dataset in my opinion, and it tells a cool story, right? This is again an example from the Rethinking book, so if you want all the gory details, please refer to the book. And the idea here is that we have measurements of population size and number of tools for several Pacific islands. So here, coming from Tonga and Fiji and all the way up here to Yak, I think is the name of that island, and all the way up here into Hawaii. So this is islands spanning a large fraction of the world. These are seafaring communities that colonized these islands in a time in human history where they had no business doing this. I mean, this is amazing. Some people describe this Pacific Island colonization as the original moonshot. I mean, this was like an investment of technology and time and effort comparable to going to the moon. This is really an amazing feat of human ingenuity. And these islands, they harbor different sizes of populations, right? Some islands are very small, some islands are very big. And they have some tool set, right? So they have fishing hooks and boats and knives and ways of making fire. And anthropologists will go to these communities and sort of quantify, like tally up what are the different technologies in these populations, right? And you can imagine that the technological repertoire of these populations depends on their interactions, right? Depends on where they are in the world. So maybe similar islands require a similar tool repertoire, and they talk to each other, right? So there's interchange here. And so islands that are close together might share tools or things like that. And what we're interested in is sort of figuring out, and crucially, tools are invented, right? And so having larger populations presumably leads to the development of more and more tools. And one theory is that tools kit size will scale with population size, right? As your population grows, you invent more things and you accumulate more tools, okay? And we're going to use this data set. This is the full data set, okay? So it's 10 observations for these cultures here, which are in different islands. We have measures of the population. We have measures of the contact rates between these populations, like how much do they interact with other communities. And we have our response variable here, which is the number of tools that these populations have in their toolkit. Okay? Does that make sense? So again, this is a fairly straightforward data set. We have one predictor and we have a count of tools. If we're modeling counts, which distribution would you choose? Poisson, okay? All right. So this is the standardized log population and tool count, and we have some sort of relation here that we would like to model, okay? I marked the populations with high contact in red and the populations with low contact in black here. So you have these two groupings of this very broad measure of how much these populations interact with each other. And the sort of first way to look at this would be to use a Poisson model, right? So this is a Poisson regression model with a log link function here and a linear regression of the log population size on the number of tools. And I'm allowing the two parameters here to change according to the contact variable, right? So I'm estimating separate regressions for the populations that have high contact and populations with low contact. Okay? Any questions? I have some pretty wonky priors here. And I will say that these were selected through simulations. So by simulating from these priors and looking at the relation between population size and tool count, I decided that these were reasonable. And the book goes through this, but try it yourself. Just take an R normal, right, in R, with these parameters, plug it into this equation for some range of population values here and see what the predictions tell you, right? And you will see that these are pretty good. They're not fantastic, but they give a reasonable final number of tools, and I think they're reasonable. But if you want a full description of this, please refer to the book. But the only way to do this is to use simulations, okay? Don't try to look at this and guess why these are good priors. Use simulations. And this is the model fit from this Poisson regression model here. And you get very wide confidence intervals. So in red here is the confidence interval for the high contact populations. And in black here, we have the fit for the low contact populations. Hawaii is much bigger than anybody else, right? Hawaii is a much bigger island, so the population is much bigger. And this model is doing okay, but again, it has some weird behaviors. So one thing it predicts is that at some point, the two lines will cross here and the low contact populations will supersede the high contact populations in number of tools, which is kind of weird, right? You would think that the interactions between populations would always lead to having more tools because you have an effectively larger population size, right? It doesn't have a lot of information in this region, so the confidence intervals are really wide. And it also has a weird behavior at 0, where it predicts a higher number of tool counts than 0 when population is 0, which is also weird. I mean, if you're modeling the number of tools depending on the number of populations, presumably if there's nobody, there are no tools. And this model fails to capture that. So the question is, can we do better than this? Like, can we define a model between the total population size and the number of tools that's a little bit more principled than just slapping a Poisson regression on a count variable, right? And what I'm proposing is that we use a dynamic model. So the idea here is that the total number of tools is something that is controlled by some input here. So the idea is that you have some innovation that produces more tools, right? And innovation comes from two things. Comes from population, right? More people in your island will lead to more innovation. Oh, sorry. More people in your island will lead to more innovation, which will lead to more tools, right? Where else can innovation come from? Innovation can come from sharing. So the idea is that talking to other populations will lead to more innovation, which in turn will lead to more tools. So contacts between populations will also increase the number of tools. Okay? But tools get lost too. There's some rate at which technologies are forgotten, they're abandoned, right? And so there's going to be some loss, which reduces the number of tools. So this is a model that has a dynamic influx of innovations and some loss here. And how do we write this? Well, we can do something like the change in the number of tools is something that scales with population. So there's some innovation rate times the population, right? But we don't want this to be completely linear. So I'm going to add a coefficient here that is something like a saturation. So this allows for very large, it's hard to increase the number of tools once your population is very large, right? Doubling the population at a small value might lead to a lot of innovation, but doubling it after the population is very large might lead to a smaller amount of new tools. So this is sometimes called an elasticity, and it functions as a saturation. As the population grows, you sort of find some set number of tools there. Yeah.
So it has to be,
Yeah.
So this value of beta has to be limited for this to happen, for it to represent a saturation, right? Smaller
Yeah, it
than
has to be
1
small.
or not
Yeah.
necessarily? Not
I
necessarily.
think that's yeah. Smaller than 1, yeah.
Smaller than what?
Smaller than 1.
Than 1,
Otherwise,
yeah, okay.
it's
that
growing,
was
right?
my,
Yeah,
okay,
exactly.
thanks.
Okay. Now we have to include the loss, right? And the loss, what is it proportional to? Well, it has to be proportional to the number of tools, right? You can only lose tools if you have them. So this is sort of a death rate of tools. So this is the birth rate of tools and the death rate of tools, and this will generate our change in the number of tools. So this is basically a difference equation for the number of tools. Okay? So that's that equation there. And how do we use this? Yeah, sure.
This equation, you are taking the delta t, the difference in the number of tools. What is the measurement of, like, temporal? You are taking the difference with respect to what? The population?
Oh, sure. Well, this is at
to
some
time.
time scale. I don't know. Because I'm going to do a trick now. I want to fit the stationary number of tools. So I'm going to set this to 0. What is the equilibrium number of tools given one of these populations, right? And if you set this to 0 and you isolate t, so when delta t is 0, you get some equilibrium number of tools that is just right? So we're going to use this dynamic model to find a steady state, right? So we're probing these populations, and they have some toolkit that they use, right, that we measured. That's not changing much. There's some cycling, but there's some stable number of tools that each of these societies uses, right? Yeah.
This model doesn't seem to capture something that you mentioned was important, that is sharing or connectivity between
we got there.
population.
Don't worry about it. Yeah. Okay. So this is the expected number of tools, right? Given this dynamic model of tool innovation and tool loss. Okay? And we're just going to plug it into a Poisson regression. So now our expected number doesn't come from the linear regression anymore. Now there's this expression here that we derived that gives us the predicted number of tools that we can use as the mean of a Poisson variable. Okay? There's no link function here, right? And so we have to make sure that this thing is positive. And we do that by setting appropriate priors in all the parameters. So the exponential prior only has density values at positive values. And so this guarantees that the whole mean will be positive. Crucially, I'm not addressing your complaint that beta should be less than 1. I'm sort of trusting that the model fit will keep it closer to 0 than to above 1, because we don't have any population with an exponential number of tools. But we could do that too if you wanted to. Turns out we don't have to. Okay, but what about sharing? Go ahead.
Isn't the way we defined lambda a link function? Like,
isn't the way we define a lambda a link function? No, a link function would be a function on lambda, right? There would be either a log here or some other function to make the estimates positive. But given that our predictor is only positive, we don't need to do that. Okay, so our predictor is restricted to the allowable values of lambda. So we don't need a link function in this case. Okay? All right. But what about sharing? So one thing we have about these islands is how far away they are from each other. So one way to approximate this sort of shared environment and shared culture and shared everything else we can't observe is to use a proxy variable. And the distance is a reasonable enough proxy variable, right? Societies that are closer together will probably have similar environments. They will also have more contact. And so we can use the physical distance across all of the islands in thousands of kilometers here as a proxy for all of these unobserved historical and cultural and environmental similarities across these guys. And how do we do that? Well, the idea is that we're going to add basically what in the multiplicative scale can be thought as random intercepts or block intercepts. So we have a multiplicative model here. If we had a usual linear model, it would be something like this, right? Alpha 0 plus the alpha for each block. Right? This is the usual random intercepts that we add to make observations in the same block more similar than observations in different blocks. In this case, since our model is multiplicative, we're going to use a random intercept that manifests here as a multiplicative constant. So we're going to have some positive number here that varies by society, and that will include this information on distance. So this is how it looks. So we take our predictions from the last model, and we add some coefficient here that varies by society, that is supposed to make close by societies more similar to each other. Okay? Yeah. We need the case to be positive. So in order to make the case positive, we're going to take the exponential of the parameter here. So the full varying intercepts in this case is the exponential of these ki's here. Okay? Yeah. Can you use the microphone, please? Is it there?
So we choose exponential to make this a multiplicative constant positive.
Yeah.
But why exponential instead of anything else that does the same thing?
Do you know any other easy to use functions that make everything positive?
Yeah.
You can use that too, the squares if you want
yeah,
to. That's fine too. Yeah.
Okay, thank you.
The idea here is just to make these guys positive. Okay? The exponential is a little bit easier because if you take the log here, then you get just the k's adding. Then you get an additive relation between the rest of the predictors and the intercepts that you're using. Okay? But again, fairly arbitrary. We just need a positive number there.
But changing the function, will it interfere in the overall distribution of parameters? No?
No, because we're going to fit this, right? So there's going to be some numerical value here that we're fitting.
Okay.
And we just need it to be stable. And so if for some reason in the computational process a negative value appears, you're going to get an error, right? And so you need it to be, this guarantees that it's going to be positive, but whatever value it lands on, that's going to be the estimate.
Okay, thank you.
So, yeah.
So just to be clear, K.
I don't know why we insist on the red microphone.
Just to be clear, K is a parameter that we're going to fit on based on our distance
we're gonna
matrix?
yes, it's going to be dependent on the distance. And I'm going to show you in a couple of slides how it depends on the distance. But the idea is that these guys should capture some aspect of the distance between the populations. How do we do that? We do that by using something called a Gaussian process, okay? And a Gaussian process is basically taking the k variables and having them be distributed like a multivariate normal with some covariance structure here. So what is this K matrix doing? The idea is that for each, so for two K parameters, it's going to be something like the variance of K1, the variance of K2, and then the covariance between K1 and K2. So if you only had two societies, this K matrix here would be something like this, in which we have some variance in the diagonal and then covariances off the diagonal. If the covariances are large, so if sigma K1, K2 is much bigger than 0, then the observed distribution, then the expected distribution between K1 and K2 is going to be something like this. There's going to be a strong relationship between these two, such that higher K1s means higher K2s. If the covariance between K1 and K2 is small, then you don't expect any relation between them. And K1 and K2 will be independent. And knowing K1 will have no information on K2. Okay? So this is what this K variable is trying to capture here. If we try to fit this with 10 communities directly, there's going to be one covariance parameter for each pair of societies. So that's on the order of like 50 parameters in this model. And given that we only have one observation per society, this is the full data set, okay? This is the whole thing. You only have one observation per society. So hopefully, you can see that estimating 50 parameters using these 10 data points is a bad idea, okay? So instead of trying to estimate the covariance between all of these random intercepts, we're going to use something called the Gaussian process, which makes the covariance between the random intercepts depend on some quadratic function here. This kind of looks like a normal distribution. That's why it's called a Gaussian process. And here, this Dij here is the distance between the societies. So what this model thinks is that societies that are close together should be more correlated, and societies that are further apart should be less correlated. How much more or less correlated? I don't know. But I'm going to estimate it using these two parameters, this eta parameter and this rho parameter. This eta parameter is related to the correlation of societies that have zero distance. How similar are societies that are on top of each other, right? That's what this parameter is measuring. And this rho parameter is how fast this correlation decays. So we have to set priors for these two parameters. And we can look at the expected covariance given these priors. So this is simulating from this prior distribution here, and I'm plotting the expected covariance for various distances, okay? So as the societies get further apart, one of these curves here is telling you how the covariance decays. So these are samples from the posterior. So in this curve here, it expects a very high covariance when societies are close together, and then it decays fast. And then societies above, let's say, 2.5 thousand kilometers are mostly uncorrelated. While this curve here has a smaller covariance, so close by societies are less similar, than this one over here, but it decays much slower. So we have long-range correlations, right? And this is sort of all the possible values given our prior for this relation between the societies. Okay? So we're using just the distance to define how similar or different the societies are in our model. And this gets away from the problem of estimating 50 different parameters for the covariances across societies by just using the distance. Like these societies are more or less different depending on how far away they are. Okay? So this is the full model. We have the expected number of tools in equilibrium given our dynamic model. We have varying intercepts that make close by societies more similar to each other. We have priors on the expected value parameters here. And we have a multivariate normal prior on the random intercepts that imposes a correlation across these guys that depends on the distance. So the Ks will be very similar for close by societies and more different for far away societies. Okay? And you can think of this as sort of a continuous block version. So each society is its own block. And the blocks are more or less similar depending on their distance. Okay? Any questions on this model specification here? Yep.
So the IF society, the I index, is related to each little island.
Exactly.
And the J index is to all of the other islands and how far they are from
Yeah, so
the
for
one.
each pair, like the covariance between islands 1 and 2 will be given by Kij. For K1, 2, this covariance between these two values will be given by this expression, which depends only on the distance between those two islands.
So you're running to all of the possible pairs of islands
Yes.
you have.
So I'm going to get one estimate for the correlation for all pairs of islands. Yes.
Okay.
Anything else? Yeah, sure.
So this shape for the Gaussian covariance that we had, eta squared,
Yeah.
it's a choice too, right?
It is, yeah.
Oh.
So this is defining the shape of this curve here. I could choose something else. So for example, one popular choice is instead of doing the square, you could have something like eta exponential of minus rho. I took the square of the distance here. This is the Gaussian part, right? It's this square term. So instead of taking the square, I could take the norm, right? And this will give something like this, which is a little bit, it doesn't have this initial slow slope here. It goes down faster in the beginning, but it has a longer tail. So you can also choose that for your Gaussian process. Another thing people do frequently is using something that is periodic. So if you have measurements that have some cycle in them, so either yearly measurements or circadian rhythm measurements, right? So maybe your two measurements are in the similar time of day, and you want them to be similar because they're taken at the similar time of day. You can choose, what people call this a kernel, right? So you can use a periodic kernel so that measurements taken at similar times of day are similar.
But we need domain knowledge then for
Yes.
this choice as well as
Yeah.
for, okay. Yeah.
Exactly. So choosing, and you can define your own kernel if you want to. And we'll see some other examples later. So this is the model in Rethinking. Pretty straightforward again. So there's a Poisson regression happening here. The lambda, the expected one, is just the expression that we had before. Doing the Gaussian, this is a non-centered version of the Gaussian process, so it has that alpha 0 plus alpha bar times sigma alpha shape, which is happening here. Yes? No, go ahead. This is complicated, so I just put it here so you guys have access to it, but I don't expect to be able to read it right now, okay? Yes?
My question is actually in the previous slide.
Sure.
So, okay, the lowercase k is a multivariate normal, and then you have this uppercase k, but below you have the kij, and this
this k is the same as this one. So this is defining the positions of this matrix. So since we have 10 societies, this is a 10 by 10.
Okay. So k, uppercase k is a matrix, and
Yes.
you are stating each element of the matrix.
Exactly,
Okay.
Exactly. Yeah.
You explained how to create the curve, and that we could use like the model of the value. This would show like different weights for the condition that we are using. Like for distance, for example, if you consider that distance is not as important as population size, for example, we could use different methods for creating the curve that will reflect that.
Well, if these guys can be as small as you want them to, right? So what this thing is setting is the correlation between them, not their magnitude. So these guys can be very small and still be correlated. In this case, if they're close to 0, then their explanation is close to 1, and they won't do much in the model, right? But what we're interested in is setting a correlation pattern. So this model, it can use the distances to make very large Ks and make societies that are close together very different from the ones that are far apart, or it can estimate very tiny Ks, and it won't make that much of a difference. But it can learn how much closer societies are more similar than further away societies. Yeah.
So now something that you said before actually makes even more sense, because since k are correlations, we want that when k is 0, they don't influence the model. So taking the exponential of k, it's actually way better than taking k squared.
Yeah, that's a good idea. You're right. Good point. Yeah, taking the exponential makes setting the prior more direct, right? Even if you had like a quadratic transformation, it would still get estimated close to 1, right? But setting the prior will be different. The prior, so using the exponential transformation makes setting the prior centering the prior at 0 the correct choice, right? While if you took the square, you would have to center the prior at 1 to have the center of the prior be the no effect of k. Good point. Is this clear to everybody that this is the distribution of possible covariance kernels, right? So this is like before I fit the data, this is what the fall off of correlation could look like. You could have very large correlations that fall off fast. You could have small correlations that fall out fast. You can have medium correlations that fall slow. You can have all of these combinations. Okay, this is the model code. And this is the posterior covariance. So this is what the model thinks the correlations fall off like. So these curves used to go all the way up to 3 here. But after we see the data, we conclude that the correlation between close by islands is much smaller than what was possible in the prior, right? So this is the model learning how similar close by islands are. And we can look at the estimated correlations in a latitude longitude here. So this is the model fit, and I'm plotting the correlations here. This is a fully connected graph, so there's a line going through every pair of society, but the blacker lines are the stronger correlations. And the lines you can't see are so close to zero that you can't see them here. So there are lines going from Hawaii to everybody else, but they're so faint that you can't see them. And this is, what is this telling us? Hawaii is so far away that the model doesn't think that there's any contact between Hawaii and everybody else, right? While these islands that are close together are very highly correlated.
Just a quick reminder, is the correlation dependent only on distance?
Yes.
Okay.
But the correlation depends on distance, but it depends using this exponential kernel here. So how fast it decays with distance and how strong it is with small distances is learned. So the model is estimating the shape of the decay. And this is the shape of the decay that the model estimated. So for very close islands, we have a correlation, a covariance around here. And as we get further away, at around, let's say, 7,500 kilometers, which is around the distance of Hawaii, the correlation is very small, right? Okay? So this is the estimated correlations. This is measuring how similar close by islands are to each other, right? And this is informing the value of the K parameters, right? So I expect the K parameter for Laos and Fiji and Tonga to be very similar, and I expect the K parameter for Hawaii and Santa Cruz to be very different. Okay?
And the information to estimate that comes from the number of tools shared by the islands and the distance.
Exactly.
Right?
Yes. And we can also look at this in the final model fit. So this is the model fit in the end. Now we have log population on the x-axis and total tools on the y-axis. These are the mean model fits. And you can see how the correlations sort of relate to the tool count, right? So these guys that have a small number of tool count are very correlated. And this is not the prediction for each island, crucially, because I'm not showing the effect of the K variables here. But you can see that these correlations inform the model fit here. And you get this. Tonga has more tools than expected for their population size. And it's kind of, the model thinks it's pulling Chuuk up, right? So this guy's pulling this guy up here. So Chuuk would have less tools if it weren't for Tonga being so close by. Yeah, well, I'm telling you this. It's hard to. So these two make the prediction for Chuuk be a little bit bigger because of this large correlation here. While Hawaii is far away from everybody else and it gets most of its tools from its very large population. Right? Okay? So what does this model do? This model includes a dynamic model and also the interactions between all the populations given using the distance as a proxy for these interactions. Yes?
The same connections that are in this graph are the same from the previous one?
Yeah, they are the same ones. Yeah. So, but this is the spatially structured one, right? So this is showing you a latitude and longitude. So you can see that close by islands are more correlated, with some exceptions here.
Yes.
So remember, the Tonga is very big, right? And so it has a lot of tools. And so the model doesn't think that it's as correlated with this other tiny island.
Yeah, so the line that you were showing before in the next graph, sorry, it's not from Tonga to Chuuk, it's from Tonga to Laos.
Fiji. Yeah, you're right, sorry. Yeah, you're right.
Yeah,
Sorry.
and Paulo said that some of this correlation is also explained by the number of tools that are shared between islands.
Well, yeah, these correlations are estimated at the same time as everything else.
No,
right?
yes, but
So they come from the same model of tool count.
yeah, but it's based only on tool count, not of tool types that are shared between islands, right?
No, because these variables here are predicting tool count. And so their value depends on tool count. It's just that the correlations between them depend on the distance. So the estimate of the value comes from the tool count, and the estimate of the correlation comes from the distance. But these are all fit at the same time, so information is shared across all these things.
This correlation between number of tools, I think what he's trying to say is that you're not taking into account that this society uses, I don't know, stones, this society uses a hammer. So it's just number of
It's just number of
and
tools,
not
yes.
the identity of the tools.
Yeah, there's no identity. Yeah, you're right. There's no identity here. Okay? This is a very complicated model. I don't expect you guys to walk out of here knowing how to do this. I just wanted to give you a sense of how you can include this structure of similarities in these models, right? And these Gaussian processes are becoming very popular. So it's cool that you guys are exposed to it at least once. So in this case, the structure for these random intercepts comes from the distance, but it can come from somebody else, for something else, right? One thing that happens a lot, and I've talked to this several times, is that we can have random intercepts that are dependent on phylogenetic models. So if we measure the same variables across several species, we expect measurements from species that are close together to be more similar than measurements from species that are further apart, because they share a large fraction of their evolutionary history, right? And this is the primate phylogeny. And we can use the phylogenetic distance the same way as we use the physical distance, right? So you can get random intercepts that are correlated according to phylogenetic distance. And this is what a lot of phylogenetic models do. They will include varying intercepts in your model such that the correlation of the varying intercepts is proportional to the amount of time that a pair of species shares, right? And so if you're looking at these two species, they will have shared all of this evolutionary time, and they're expected to be very highly correlated. While if you take these two species, like one here and one here, they only share this tiny branch at the bottom here. And so they're expected to be less correlated, right? And you can define a K matrix. Instead of using this Gaussian process here, you can just define a K matrix that is proportional to shared evolutionary time. And that's what usual phylogenetic models will do. There's also a broad class of models called animal models that do a very similar thing, but using pedigree information. So if you have two individuals in a pedigree, so this guy is the son of these two, and this guy is the daughter of these two, and you can write out an expected correlation between any two pairs of individuals given the shared relation, family relation between them, right? So two brothers, for example, these two will share 50% of their genome, and so you have some expectation of the correlation between measurements in these two individuals. And I put a little reference here, an ecologist's guide to the animal model, which is a very good introduction to this class of models, which again are the same thing. You're just setting random intercepts and setting the correlation across the random intercepts to be proportional to some other thing that you know. In breeding designs, you usually have the pedigree information. But today, in genomic studies, it's much more common to estimate these relationships using genomic data. So you might have something called a GRM, a genetic relatedness matrix, which is just the correlation between genetic variants that you measure in two individuals. And so a GRM matrix is just an an estimate using genetic information of how much of the genome two individuals share. And as they share more and more of their genome, you expect it to be more and more similar. And you impose this in your model by using random intercepts or random slopes that are correlated according to the genetic sharing between these two individuals. Yes?
I just want you to go back to the phylogenetic models and explain it a little better.
Yeah, sure. So you can use this phylogeny to define a distance. And usually what people do is say that species are more similar if they share an evolutionary history. So for example, for these two species here, coming from this branch and this branch, they share from the root up until this knot here. So this is the shared amount of evolutionary history between these two species. From here to the root. And as species share more of their evolutionary time, you expect them to be more similar. And so you transform this matrix into sort of a correlation matrix like this. Yeah.
Como é mais ou menos
It's fine in Portuguese. It's fine.
Okay. I would say like the closest species has a zero distance, and then like how would I do that?
Yeah, you can do this on the distance scale or the covariance scale. The covariance scale is a little bit simpler. So people will say that if you share your full evolutionary history, then you have a covariance of 1.
Okay.
And as you have to look at the distance between the most recent common ancestor between the two species, the pair of species that you're looking at, and the root. So what fraction of this full distance here is shared? So if they share 80% of the distance, you might say that the covariance is 0.8 or something, or proportional to 0.8. Then you have a variance parameter, basically. So the correlation is going to be 0.8, and the covariance is going to be dependent on the variances that you estimate. So it's proportional to. So if it's the same species, correlation of 1. If it's a related species, correlation proportional to how much evolutionary history they share. That's about the idea. Yeah.
Well, in the example you gave previously, you added this matrix as a multiplicative factor.
Yeah.
But how would we do when we have phylogenetic distance?
Well,
What would we do?
are you talking computationally in the model?
Yes, we would be modeling like 2 traits, for example.
Sure. Just
And
like we
then-
did here, right? It's
Yes,
2
and-
traits, but the measurements are structured by distance. In a phylogenetic model, you would have 2 traits, and the correlation within each one of these species would be more similar if the species were more similar, right? Is that what you're thinking about?
Yes, and it would be a multiplicative factor as well.
No,
In-
not
in that-
necessarily.
In that example for
Think about the island example that we saw in the practice today. So we have the slopes and intercepts for each archipelago, right? And in that case, you had some information sharing across archipelago, but you could also have it so that archipelagos that are closer together are more similar than archipelagos that are further apart. You had no correlations between the slopes and intercepts across different archipelagos in that example. But you could also say that closer together archipelagos are more correlated. And now you have a slope and a regression between islands size and island richness within each archipelago. And the estimate of that regression could be correlated across archipelago. And that correlation could be proportional to some distance. Does that make sense?
So we don't need that step when we
What step?
propose
Sorry, I can't see
the
what you're
delta
pointing.
t.
This thing?
Yes.
No, this is a model that was specific for the tool innovation thing here. So
Okay,
this
I
is
was thinking about we would have to get a model like this, and then add a multiplicative factor.
No.
that-
So if you have, let's write it. I should have written out a model definition there. But if you're doing a linear regression between two variables, like in the island example, you can do something like this. So it's going to be yi as a function of a normal mu sigma. And this is structured in populations somehow, right? And now you can write the expected mean as a set of slopes, alpha 0 plus alpha I, set of intercepts, varying intercepts per species, so I put a J here, plus beta plus beta J per species times the predictor. And these guys can be multivariate normal with a mean of 0 and some K matrix with a scaling factor here. This would be a standard phylogenetic model. And this guy is proportional to the phylogeny. And so each J here is a species, and the correlation between these J's comes from some structuring, some distance that structures the correlation. It can be distance in the archipelago. It could be phylogenetic distance if you have measures for several species. It can be genetic relatedness if you're measuring related individuals.
In this island example, that's the final.
Yeah. That's not the prediction.
Yeah,
I could also put, this is excluding the K's here. I'm just plotting the expected, this guy here without the K.
The curve?
Yeah, the curve here doesn't include the K's. But then for each island, if I wanted to get predictions for each island, I would have to multiply by the K of that island. Okay?
Okay.
So this is the mean prediction. It's not the individual island prediction. But this mean prediction happened while estimating the K's simultaneously. So while the estimates are not shown here, this mean line was predicted in the presence of the K's.
Mm-hmm.
Okay? So if I had like an island all the way up here, the leverage of that island could be absorbed by the K's and not the mean prediction. So it makes the mean prediction better.
Well, I was just wondering about on the first times that you plotted this, you had the categories of islands, so the islands that had high or low contact.
Yeah, we replaced the high-low contact by the continuous distance.
Okay. That was my...
Yeah, sure. Sure.
So I would just like to know about the distance. We are talking about the distance. There is any metric.
Yeah, kilometers.
Is it an Euclidean distance, or which metric is be using?
The distance in the island example? Is that what you're asking?
In the model, the distance d that we are considering. Yeah.
Sure. That distance comes from this distance table here, which is just pairwise distance between the islands in kilometers. Thousands of kilometers. So it's just the physical distance between the islands. Okay. Yes.
But this distance could be a similarity
Sure,
distance.
it can be something else.
Yes.
Instead of using physical distance, we can use whatever other measure of distance we want to. You can even add two distances in the same model if you wanted to. You can have like a coefficient here for some other distance. And you can measure which one of them is more important or something. Okay, and I told Paulo several times that I wanted to show all of these different correlated residual models here, not so you guys understood all of them, but so that you understood that they were the same model. And so if you see them in the wild, you might not understand any of them, but your ignorance is reduced by knowing that they're the same thing, right? When you understand one of them, you will understand all of them. And so it's good to know that they're all the same thing. Okay.
I'm just still wondering about the islands case. So, like, what type of inferences would you make from that model? Because, like, the mathematics behind it work wonderfully, but I feel like maybe this is just a type of modeling that, I don't know, doesn't translate into a lot of information.
Well, now you have here an expected relation between the number of the population and number of tools, which is exactly what we set out to do. So this is the model fit. Like, this is the expected rate of innovation in the number of tools given population size. Isn't this the relation that we were after?
Yes.
Okay.
Yeah.
Good. And it includes all of the cultural and sharing and all that. Maybe you don't think it's interesting. That's fine. But
No, yeah, I was just thinking like something of like a phylogeny between islands would be more interesting, but it's another, yeah.
yeah, sure. That would be cool.
When building the full model, you didn't include the contact rate. It's it's either low or
I
high.
replaced the contact rate by the distance. So instead of having this binary high-low contact, I estimated the contact using the distance.
Yes.
And this is what's happening here, right? So it's not just that these islands have high and low contact, they have some level of contact across all of the other islands, right? And so maybe Hawaii is definitely low contact because it doesn't have any contact with anybody else. But maybe Chuck is intermediary. It's not just high or low, it's some intermediary level here. It has high contact with Yap and Manus and low with everybody else, right? So now you have a continuous measure of contact.
But you could also add this.
Also add the predictor, sure, you could, yeah. Anything else? Okay, I'm satisfied. Thank you, guys.